Damien Huerta, my partner is Nathan Wang, and this is our final project for Fundamentals of Machine Learning. Methodology. The Olive dataset has around 32,000 samples, and our team decided to classify these using k-means, Gaussian mixture models, k-nearest neighbors, and convolutional neural networks. One of the big components of our methodology for the first three classifiers is using autoencoders, since using the original size images was far too big in the feature space, so we decided to use an autoencoder, a custom autoencoder that we implemented that reduced the features to 50. And on the right-hand side, the figure one shows a reconstructed sample image from our trained autoencoder. The left-hand side is the raw, and then the right-hand side is the reconstructed image.
So in terms of creating these models, for k-means, we use the sklearn library, and we tested with multiple clusters and classes. We ended up using 3 clusters. And in terms of GMM, we also used the GMM class in sklearn, and we tested with 3. We ended up using 3 classes as well, but we also tested with different types of covariances, such as tide, full, diagonal, and spherical. We ended up using the tide covariance. And in terms of KNN, we use a simple approach to classify based off of K neighbors majority vote, and we utilized 50 feature samples and tested over various K values to maximize accuracy. In terms of CNN, our initial approach was revolving around ResNet. However, we pivoted to a custom CNN architecture based off of AlexNet. We also experimented on different types of loss, such as cross-entropy loss, MSE, and focal loss, and we also incorporated dropout to combat overfitting. So after running the k-means model, we found with autoencoders, we got a 43.87% accuracy, and that the overall algorithm predicted 77.9% of all samples with a true class 1 as class 1. However, it was unable to predict class 0 and class 2 correctly. The reason behind this could be due to the model seeing all the images as one big cluster, and that the images themselves could have poor image quality and poor orientation. So when testing the GMM model, we found that it performed better than k-means with a 50.6% accuracy. However, there were still stability issues when using a flattened image, and that's why we decided to use an autoencoder. Whenever we did this, we found that the overall model predicted the true label 0 correctly. However, it still struggled to predict true label 1 from 0. The big reason behind this could be just poor image quality.
KNNs. We experimented with various K values for the majority vote, and we found that K equal to 4 performed the best with our encoded samples again. The model predicts label 1 as samples that have true label 1 as label 1 with 63.83 accuracy and an overall accuracy of 44.7, which is an improvement of the 38.4 accuracy that we achieved when implementing KNNs with the flattened images. So you can see it kind of incentivizes the use of the autoencoder and the reduced features to improve our performance and accuracy. CNNs. We initially started our approach with convolutional neural networks with implementing existing architectures such as ResNet, and obtained a 44.9% accuracy and a 75.3 training accuracy, but experienced a bit of overfitting, and we wanted to have a little bit more control of that, so we implemented our own custom CNN. We named it ONET. Figure 5 shows a model summary of ONET, and figure 4 shows the learning curve of the training for the model, and then also the accuracy of the training and validation during the training of the model. As you can see, there's still kind of an overfitting issue here, despite us ranging our dropout drastically from various execution runs. We couldn't really combat this and close the gap as much as we would like to, but we are able to achieve a testing accuracy of 51.06, which is the highest that we obtained for all of our classifiers. We did this with 0.2 dropout using focal loss to emphasize the importance of classifying hard to classify examples, and we use the Atom optimizer. Conclusions. This image, figure 7, shows the correctly predicted samples per classifier. As you can see, different models perform well on different classes. For example, GMMs does a pretty good job of classifying class 0 and class 2. That's kind of important because class 2 also has the highest severity for the disease in question. So you can see we predict 1,227 of those samples as class 2. And k-means performs the best in terms of correctly predicting class 1 with the number of samples. And CNN and KNNs kind of are in the middle of those two. We believe part of the issue with GMM's inability to predict the class 1 samples correctly is just one big cluster being in the middle of class 1 that kind of seeps into class 0 and class 2. And the reason for this would be that the training data has a very bad distribution of class representation. As you can see, class 1 represents nearly half of the overall training data, but GMMs is able to catch 80% of the class 2 cases as class 2 and 91.09 of the class 0 samples as class 0. And K-means performs the best for class 1. So we can see there's kind of a trade-off between each individual classifier.
So in terms of future works, the team could work on overall exploration of feature selections, such as PCA. They can also work on a combination of multiple different types of classifiers. They can also work with data set distributions and improve their overall CNN architecture.